Let's study 9th standard ICSE Physics, Chapter 2B and C, Graphical Representation of Linear Motion. First, let's study some displacement time and velocity time graphs. Graphs are an easy way to calculate things like displacement, velocity, acceleration, etc. It also helps us to analyze the motion. When we'll do the numericals, we'll discover the usefulness of graphs. But looking at the shape of the graph, we should learn how to determine what kind of motion is it. Is the object stationary? Is it moving with a uniform velocity? Is it accelerating or decelerating? This can be ascertained by looking at the graph. Note that this is a graphical representation. This is not the actual trajectory of the object. The object isn't following this path in reality. This is just a representation of the motion, not the actual motion. So let's talk about displacement time graphs first. When you see a horizontal line which is parallel to the x-axis, which is always taken as time, we can be sure that this object is stationary. Suppose the displacement here is 30 meters. So after every 1 second or every unit time, the displacement continues to be 30 meters. That means it's not moving. It has zero velocity. But what if you see a straight line passing through the origin? A straight line which is inclined to the x-axis represents uniform velocity away from the origin. So after 1 second, let's say the displacement was 10. After 2 seconds, the displacement was 20 meters. After 3 seconds, the displacement was 30 meters, and so on. So equal displacement in equal intervals of time means uniform velocity. And since the displacement is increasing, means the object is moving away from the object. On the other hand, a graph with a negative slope represents again uniform velocity but towards the origin, which means, say initially at the beginning of the observation at time 0, the displacement is 30 meters. After 1 second, the displacement becomes 20 meters. After 2 seconds, the displacement is 10 meters, and so on. So again, it is covering equal displacement in equal intervals of time, but it is moving towards the object. So this is again uniform velocity towards, hence it is called negative slope. This is a positive slope. Note that when I say that it is moving towards the object, I'm not saying that the velocity is decreasing, and here the velocity is not increasing. It simply means that this is uniform velocity and going away, and this is coming back towards the origin, and we assume the starting point or the origin. Velocity is uniform. In fact, since the direction has changed, while doing numericals, we would say that velocity is minus 10 meters per second, where the minus sign means it is moving in the opposite direction. But what if the slope is not constant for the entire graph? What if it's a curved graph? What does that mean? It means that after 1 second, it traveled 5 meters, but after 2 seconds, it traveled 10 meters away. So totally 15 meters away. And after 3 seconds, it was, let's say, 30 meters away. So it is not covering equal displacement and equal intervals of time. That means velocity is not uniform. So it's non-uniform velocity, which is acceleration. So these are the displacement time graphs. Now let's study the velocity time graphs. But before that, a few points to note here are, the graph cannot be a vertical line. It cannot be parallel to the y-axis, because that would mean it can cover infinite displacement in 0 time. That's impossible. That means it has infinite velocity. That is not practically possible. Also, what if the graph goes below the x-axis? What would that mean? Well, that would mean that now the object is moving in the opposite direction. It has reached the origin back, and now it is moving totally in the opposite direction. So now the graph would be calculated negatively. For example, after 4 seconds, the displacement is minus 10. After 5 seconds, the displacement is minus 20. What is the meaning of minus here? Well, displacement can be negative. It's a vector quantity, and it simply means that we are calculating now in the opposite direction. So that is what it means. When we do numericals with these graphs, it will become clearer what is the significance of the slope, the positive and negative values, etc. Now in velocity time graph, again, we have a few varieties. a horizontal line to the x-axis means it is uniform velocity. Now notice how in displacement time graph this represented uniform velocity, but in velocity time graph the horizontal line represents uniform velocity, because if it is a 30 out here, that is 30 meters per second, that means after 1 second the velocity was 30 meters per second, even after 2 seconds the velocity remained the same, and even after 3 seconds the velocity was constant, uniform velocity, no acceleration, moving in the straight path in the same direction, uniform velocity. Here horizontal line meant stationary, but not here, because it's a VT graph. So be very careful about whether it is a VT graph or an ST graph. If I were to draw a VT graph for a stationary object, then it would simply be a horizontal line overlapping with the x-axis, because velocity will be 0. So the graph would look empty if I were to draw a VT graph for a stationary object. Now here a positive slope straight line means uniform velocity. But here a positive slope means uniform acceleration. Let's see how. So initially velocity is 0. After 1 second, the velocity became 10 meters per second. After 2 seconds, the velocity became 20 meters per second. After 3 seconds, the velocity became 30 meters per second, and so on. That means the velocity is increasing with time. That is an acceleration. And the increase in velocity is equal per unit time. So that's uniform acceleration. For example, an object falling down. It has uniform acceleration of approximately 10 meters per second square, or 9.8 meters per second square to be more precise. Now what is the meaning of the negative slope graph here? It means that initially the velocity was 30, then it decreased to 20, and then it became 10 after 3 seconds, and so on. So velocity is decreasing. So that is retardation or deceleration, negative acceleration. Negative slope means negative acceleration, and the change is equal in equal intervals of time. So that is a uniform deceleration. But note that a negative slope does not mean that the velocity is decreasing, that the direction has changed. Here the velocity is decreasing, but the direction has not changed. It is still moving in the same direction. Let me give an example. If I throw the object up, initially its velocity is 30 meters per second. Then as it rises up, it slows down 20 meters per second, 10 meters per second, 0 meters per second. So that is a deceleration. That is a uniform deceleration. Its graph looks like this. But has the direction changed? No, it's still moving in the same direction. So unlike ST graph, where a negative slope means change in direction, but in VT graph, negative slope does not mean change in direction. It simply means velocity is decreasing. But what if again it goes below the x-axis? What would that mean? Well, now if it goes below the x-axis, then I can say that the velocity is negative, minus 10, minus 20, minus 30. And negative velocity means the direction has changed. So only when the graph is below the x-axis, in this case, do we say the direction has changed. But above the x-axis, the direction has not changed. In fact, if the direction is changing, minus 10, minus 20, minus 30, if you notice, as it goes down, its velocity is actually increasing. Minus 10, then minus 20, then minus 30. Velocity is increasing. What is the meaning of minus sign? It simply means the direction is opposite to the initial direction. That's all it means, as far as velocity is concerned. And as far as displacement is concerned, again, the direction has changed. Now, here we assume that the velocity was initially 0. It was at rest. What if it was not at rest? What if it was initially at 20 meters per second, then it changed to 30, then after a couple of seconds it became 55. So even that is possible. We can plot such a graph. But here I can see that the graph is curved, which means that the velocity is not increasing with equal amounts in equal intervals of time. So it's a non-uniform acceleration. For example, a car moving on a highway, the acceleration need not be uniform. So these are the basic graphs, and we need to remember what graph represents what kind of motion. Now I often talked about the slope. Generally speaking, slope simply means how steep or gentle it is. But mathematically, slope has a formula. We can calculate it using a formula. We can derive a lot of things from the information given in the graph. For example, from an ST graph, I can calculate the velocity. Or from a VT graph, I can calculate the acceleration or the displacement. But how do we calculate that? For this, let us take a few examples. So we have two graphs here. One is an ST graph and one is a VT graph. Let's analyze the data given here. This is in meters, time is in seconds, velocity is meters per second, and again the time is in seconds. Now what's happening here is the displacement was 0, then after 6 seconds, the displacement was 60 meters. That means the object is moving away from the origin. And in 6 seconds, it covered a displacement of 60 meters. So I would say the velocity here is 60 divided by 6, 10 meters per second. So from a displacement time graph, we can find the velocity by calculating the slope. Now mathematically, the formula of slope is y2 minus y1 upon x2 minus x1. Where we take any 2 points, let's take this as x1 comma y1 and any point as x2 comma y2. You see, any point on a graph has its coordinates, the x coordinate and the y coordinate. Then we substitute the values and we get the answer. But in physics numericals, we shall use an easier method. We will simply say that the velocity is the slope, but the formula we'll use for the slope, just to simplify, is height upon base. That's it. What is the height out here? It is 60 meters. 60 meters is the height. So 60 meters. And what is the base here? 6 seconds. So the answer is 10 meters per second. Simple. That is the velocity for the first 6 seconds. But what about the remaining 8 seconds? What was the velocity then? Now I can see that from 60 meters, finally the displacement is 0. That means that the object has come back to the original place. That means that in the end, the total displacement is 0. Whenever the graph touches the x-axis in an ST graph, it means the object has returned to the origin. So let's calculate the velocity here. Again, velocity will be equal to slope. I'll put a negative slope here because it is inclined this way. It is creating an obtuse angle on the right hand side with the x-axis. So obviously if it is moving in the opposite direction, the velocity has to be negative. Negative simply means opposite direction. It doesn't mean that the velocity is decreasing. In fact, it is uniform velocity again because it's a straight line. So again, the height is 60 and that time, this time is 8 seconds. We get the answer as 30 upon 4, 15 upon 2, 7.5 meters per second. In fact, it's minus 7.5 meters per second. So if they ask you what is the velocity from time 6 seconds to 14 seconds, the answer is minus 7.5 meters per second. Negative sign means it is moving towards the origin. Now what is the overall velocity, by the way? The overall velocity, well, without calculation you can say it is 0 because the displacement is 0. If the object has come back to the original position, that means the overall velocity is 0. So what we've learned is that from a displacement time graph, by finding the slope, which is height upon base, we can find the velocity. But keep in mind the fact that a negative slope means negative velocity. And also one more fact is that when the graph touches the x-axis, that means the object is back to the origin. So at that point of time, we say the total displacement is 0. Now velocity time graph. This will be a little more advanced than this calculation, but we are ready for it with the basic knowledge that if I see a positive slope, it means it is uniform acceleration. It's a VT graph. Here the uniform velocity is shown by the positive slope, but here it is uniform acceleration. Its velocity is increasing. Velocity was 0, then velocity increased to 5 meters per second. So for the first 3 seconds, there was acceleration. Then in the next 1 second, there was deceleration, retardation. And then the velocity once again increased to minus 5. Now here minus means direction has changed. This negative slope does not mean that the object is coming back. That was in displacement time graph. In velocity time graph, negative slope simply means retardation. It means, suppose a car was moving, accelerating, and then the brakes were applied, and then it is decelerating, and comes to a stop. So from the beginning till the end, did the direction of the car change? No, it didn't. But initially it accelerated, and then it decelerated and came to a stop. Now if I plot this on a graph, it looks like this. This is not the actual motion of the car. This is just a graphical representation of its velocity with respect to time. So acceleration and deceleration or retardation, as long as they are above the x-axis, it means it is moving in the same direction. When it came and touched the x-axis, that doesn't mean that it has come back to origin. That was in the case of displacement time graph. This is velocity time graph. There's a difference between the two. It will take time for you to digest this, but you'll have to train your mind. And when we'll do numericals, you'll get well versed with it. How to remember the difference. Now, since it is going below the x-axis, now it means that the direction has changed. Now it's negative velocity. It was moving in the opposite direction. And then what happened between 5 seconds and 8 seconds in the time interval of 3 seconds? It's a horizontal line, means it's a uniform velocity. It has not come to a stop. It is not stationary. Horizontal line in a ST graph means stationary. Here it means it is still moving with a uniform velocity of 5 meters per second, or rather minus 5 meters per second. Minus means in the opposite direction. Has it come back to the origin yet? I don't know. We cannot find out just by looking if it has come back to the origin. We can calculate and discover this. So we'll do the calculation in a bit. Now again, from 8 to 9 seconds, what is happening? Look at the graph. Minus 5 meters per second velocity became 0 meters per second. What is the meaning of 0 meters per second? It means for that fraction of a second, the vehicle came to a stop. Which makes sense. See, initially it was accelerating, then it was decelerating, then it came to a stop, then it changed its direction, and then again it started accelerating, which is shown by this graph. Then it moved with a uniform velocity, which is horizontal line. Then again it started decelerating and came to a stop. That is why it's touching the x-axis. When VT graph is touching the x-axis, means for that moment it has come to a stop. It doesn't mean it has come back to the origin. That happens in ST graph. So what happened at 9 seconds? Again it changed direction. And again it is accelerating. So now it is again moving in the original direction. So the graph is above the x-axis, because it is in the right direction. For this period, it was moving in the opposite direction, so we took it negative, opposite to the original direction. It is accelerating. Again, it reached 5 meters per second. Then, from 10th second to the 12th second, for 2 seconds, it was moving with uniform velocity. Then it applied brakes, it decelerated, and on the 13th second, it came to a stop. So in the end, where is the object? How far is it from the origin? Is it back to the origin? That we cannot guess by looking at the graph. That we'll have to calculate. What is this fellow doing? Accelerating, decelerating? Maybe he bought a new car. He's just going for a test drive and checking all the mechanisms like acceleration and the brakes, etc. And looking at how quickly it changes its direction. It might be a Ferrari or a Lamborghini. All the velocity is too less, 5 meters per second. Now from an ST graph, the slope helped us to calculate the velocity. In a VT graph, the slope will help us to calculate the acceleration. What is the acceleration for the first 3 seconds? Now algebraically, we would have used the formula A is equal to V minus U upon T. Final velocity is 5, minus initial velocity is 0, upon time is 3 seconds. That is 5 meters per second square. But using a graph, how to calculate? Let's find the slope. Acceleration is equal to slope. And slope, I gave you a hint, is nothing but the height upon the base. Height is how much? 5. Base is how much? 3. Sorry, 5 upon 3 here. So here also 5 upon 3 meters per second square. So the answer comes out to be the same, which is 1.67 meters per second square. Always write the final answer up to 2 decimal places. No mixed fraction allowed in physics and chemistry. What about the deceleration of the 3rd to 4th second? If I use the formula, it becomes initial velocity was 5, final velocity is 0. So 0 minus 5 upon 1 second. That becomes minus 5 meters per second square. But we write the final statement like retardation is 5 meters per second square. When you talk about retardation, no need to put the negative sign there, because retardation by definition is a negative acceleration. But if we calculate using the slope, it would be height is 5 and base is 1. So same answer. But yes, it's a negative slope, so don't forget to put a minus sign. So you see, graph also can be used to calculate very quickly and easily. We just have to train ourselves in this. Similarly, we can find the acceleration and deceleration here. Now, point to be noted here is that when the line is horizontal, the graph is horizontal, it means acceleration is 0. Slope is 0. There is no slope. That's because it's a uniform velocity. The velocity is not changing, so obviously acceleration will be 0. So now we have learned that by finding the slope of a graph, of a VT graph, we can find the acceleration. But VT graph can also give us the displacement. And to calculate displacement from a VT graph, we just have to find the area under the graph. Area under the graph. What does that mean? If I ask you what was the total displacement after 4 seconds, Fine. Calculate this area of the triangle. So displacement after 4 seconds, that is from I'll say 0 to 4, is area under the graph, which is half into base into height. The area between the graph and the x-axis will give you the displacement. That's the beauty of a VT graph. Algebraically, if I had to calculate the displacement, then the equation would be displacement is equal to ut plus half at square. More about this formula later. But right now let me teach you the graphical method. Then I'll teach you the formula method. In exam you can use either. So displacement from 0 to 4 seconds is half into base into height. That is half into base is how much? 4. Height is 5. 10 meters. So this is 10 meters displacement. Then the car turned around. And now this is below the x-axis, means this displacement is a negative displacement. So displacement from 4 seconds to 9 seconds. It's a trapezium. Trapezium formula is half into sum of parallel sides into the height. That is the distance between the parallel sides. That is half into, this is 5 and this is 3. And the height between them is 5. Actually it's minus 5, but minus I'll add later. So what's the answer? 8, half of that is 4, 4 into 5, 20 meters. So first it went 10 meters forward, then it went 20 meters backwards. That means it has not come back to the origin. In fact, it has gone behind the origin, which we could not guess by looking at the graph. We have to calculate it. Here it's easy to know where the object is in a displacement time graph. If it has touched the x-axis, means it's back at the origin. If it's below the x-axis, means it has gone behind the origin. So let me put a minus sign out here, because it was in the opposite direction. And what about this displacement? Again, displacement 9 to 13. Again, it's a trapezium, so same formula. This is 1, 2, 3, 4 plus 1, 2 into height is 5. That's 6 is 3, 15 meters. So 10 meters, then 20 meters, and then 50 meters. So what is the final displacement of the object? 35 minus 20, 15 meters from the origin. No, sorry. 25, 5 meters from the origin. That's the final displacement. So ultimately the car was moving for 13 seconds and it managed to just cover 5 meters in the right direction. So now we know how to calculate the displacement from a VT graph, find the area under the graph. Okay, what if the question was how much distance is covered? Now distance is different from displacement because in distance we don't have any negative values. So the total distance covered is 10, 20 and 15, that is 45 meters totally. Total distance covered is 45 meters and 5 meters is the total displacement covered. Now understand that this is not the actual path of the car, this is just a graphical representation of its velocity. Also remember, the negative slope of a VT graph does not mean the change in direction. It is moving in the same direction, but it is decelerating. Only if it is below the x-axis, we say it has changed the direction. So we'll be doing many numericals like this.
Physics Chapter 2, Section B, Graphical Representation of Linear Motion. Cancel these paragraphs. Even this is cancelled. Case 1. Now we have to focus on the diagrams. The theory is not so important if we understand the diagrams well. So as explained earlier, let's talk about ST graph, displacement time graph first of all. If the object is stationary, horizontal line parallel to the x-axis. Next, ST graph with a positive slope. That means it's a straight line from the origin. It was at the origin, but now it's moving with uniform velocity. Here, if we find the slope of a graph, we can find the velocity. It's always height upon base. So if you take here, the total displacement was 50 meters and in 5 seconds. So if you divide it, the answer is 10 meters per second. We will solve numericals based on this soon. Remember, steeper the slope, more is the velocity. What is the negative slope? Well, it means that it is coming back to the origin. So if it touches the x-axis, it is back at the origin and the total displacement is 0. Notice that it is still uniform velocity. It is not retardation. It's an ST graph. And a curved graph like this means it is variable velocity. That means it's an acceleration in the vehicle. We find the slope of such a graph by drawing a tangent at a particular point. So the value changes from point to point. But such calculations are not in syllabus. Conclusions need to be studied. So wherever I've marked not IMP, you can mark it as read or not IMP, which means you don't have to study them. You can just read them. Here, this paragraph, even this paragraph, this paragraph. Now VT graph, cancel all of this. Let's start with this graph. So here we have a horizontal line. In ST graph it meant it was stationary, but here it means it is moving with uniform velocity, parallel to the x-axis. And from a VT graph, we can find the displacement by calculating the area under the graph, that is between the graph and the x-axis. Here it's a rectangle, so that's easy to calculate. Another case, if it is a straight line, that means it is uniformly accelerated. Notice how the velocity keeps on changing. First it was 10 meters per second, then 20, then 30, finally 80 meters per second. Again, if I find the area under the graph, which is a triangle in this case, I can find the displacement. And if I find the slope, I can find the acceleration. Slope is always height upon the base. That is one of the methods of finding the slope. That is 80 upon 8. The answer is 10 meters per second squared. So remember, slope of an ST graph gives us the velocity, but slope of a VT graph gives us the acceleration. What if there is a negative slope like this? This means there is retardation or deceleration. Negative acceleration does not mean that it has changed its direction. It is still moving forward in the real world. This is just a graph. Don't confuse this with ST graph. In ST graph, a negative slope meant that it is coming back to the original position, but not here. So here when it touches the x-axis after 4 seconds, it doesn't mean it is back at the starting point. It simply means its velocity is 0, so that it has come to a stop. What if we have a positive slope but not starting from the origin? That simply means that it was not initially at rest. It already was moving at 10 meters per second when we started this experiment. Now let's understand this graph. What's happening here? It's a VT graph, first of all. You have to be very clear about that. It's not an ST graph. So positive slope means acceleration, retardation. Then if the graph goes below the x-axis, then it means that the direction has changed and it's moving in the opposite direction. So again, this means acceleration in the opposite direction. Horizontal line always means uniform velocity, but since it's negative, it means it is still moving in the opposite direction to the original one. Now again, it's moving towards 0. So this is deceleration. Now it's acceleration. Now just because the graph touched the x-axis at this point doesn't mean it has come back to the original position. That happens in an ST graph, not a VT graph. This is again uniform velocity and this is deceleration. So if I want to find the deceleration in the last 1 second, I find the slope of the graph. And remember, the answer of negative graphs is always negative. So the retardation would be something like minus 5 meters per second squared. Although while writing the final answer, we don't put the minus sign if we're using the word retardation. Let's understand what's happening in this graph. So it was uniformly accelerating, then suddenly it started uniformly retarding. It seems like there was a ball which was falling down towards the earth, and after 5 seconds it hit the earth and it changed its direction completely and started retarding, going upward. So this is downward motion and this is upward motion, and the 5-second mark is the time when it reversed its direction. That is why this is below the x-axis, because it is now moving in the opposite direction. AT graphs or acceleration time graphs are not supposed to be in syllabus. The conclusions of the VT graphs have to be studied. Remember, we can never have a graph, a VT or an ST graph, which is vertical or parallel to the y-axis, because that would mean that the velocity is infinite. And imagining infinity is insanity. AT graphs, well, if it's a horizontal line coinciding with the x-axis, it means acceleration is 0, which could mean anything. It's stationary or moving with uniform velocity. But if it is a horizontal line parallel to the x-axis, this means it is uniformly accelerated. If it's negative acceleration, the graph will be below the x-axis. If you find the area under the graph, we can find the velocity. Finding slope of AT graph is of no use. This is a VT graph again, uniformly accelerated. This same graph looks like this for an ST graph, uniformly accelerated. And an AT graph, it looks like this. So all these 3 graphs represent the same motion, a freely falling body. Freely falling means without any air resistance, where g's value is taken as 10 meters per second squared. More about acceleration due to gravity in another section. Here I can see that displacement is directly proportional to square of time. Not very important from numericals point of view. So you can mark this entire section 2.8 as read, because it's unlikely to come in exams. We don't have any numericals based on AT.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.